James Hopwood JeansThe. The mathematical theory of electricity and magnetism. The law of force between charged particles. 15. The torsion balance. Coulomb devised an instrument known as the torsion balance, which enabled him not only to verify the laws of attraction and repulsion qualitatively, but also to form an estimate of the actual magnitude of these forces. The apparatus consists essentially of two light balls, A, C, fixed at the two ends of a rod which is suspended at its middle point B by a very fine thread of silver, quartz, or other material. The upper end of the thread is fastened to a movable head, D, so that the thread and the rod can be made to rotate by screwing the head. If the rod is acted on only by its weight, the condition for equilibrium is obviously that there shall be no torsion in the thread. If, however, we fix a third small ball, E, in the same plane as the other two, and if the three balls are electrified, the forces between the fixed ball and the movable ones will exert a couple on the moving rod, and the condition for equilibrium is that this couple shall exactly balance that due to the torsion. Coulomb found that the couple exerted by the torsion of the thread was exactly proportional to the angle through which one end of the thread had been turned relatively to the other, and in this way was enabled to measure his electric forces. In Coulomb's experiments, one only of the two movable balls was electrified, the second serving merely as a counterpoise, and the fixed ball was at the same distance from the torsion thread as the two movable balls. Suppose that the head of the thread is turned to such a position that the balls, when uncharged, rest in equilibrium, just touching one another without pressure. Let the balls receive charges E, E', and let the repulsion between them result in the bar turning through an angle theta. The couple exerted on the bar by the torsion of the thread is proportional to theta, and may therefore be taken to be kappa theta. If A is the radius of the circle described by the movable ball, we may regard the couple acting on the rod from the electric forces as made up of a force F, equal to the force of repulsion between the two balls, multiplied by a cosine of 1/2 theta, the arm of the moment. The condition for equilibrium is accordingly A times F times cosine 1/2 theta equals kappa theta. Let us now suppose that the torsion head is turned through an angle phi in such a direction as to make the two charged balls approach each other. After the turning has ceased, let us suppose that the balls are allowed to come to rest. In the new position of equilibrium, let us suppose that the two charged balls subtend an angle theta prime at the center, instead of the former angle theta. The couple exerted by the torsion thread is now kappa brackets theta prime plus phi, so that if F prime is the new force of repulsion, we must have A times F prime times cosine 1/2 theta equals kappa brackets theta prime plus phi. By observing the value of phi required to give definite values to theta, we can calculate values of F prime corresponding to any series of values of that prime. From a series of experiments of this kind, it is found that so long as the charges on the two balls remain the same, F prime is proportional to cosec squared 1/2 theta prime. From which it is easily seen to follow that the force of repulsion varies inversely as the square of the distance. And when the charges on the two balls are varied, it is found that the force varies as the product of the two charges, so long as their distance apart remains the same. As the result of a series of experiments conducted in this way, Coulomb was able to enunciate the law. The force between two small charged bodies is proportional to the product of their charges, and is inversely proportional to the square of their distance apart. The force being one of repulsion or attraction according as the two charges are of the same or of opposite kinds. 16. In mathematical language, we may say that there is a force of repulsion of amount C times E prime over R squared, where E and E prime are the charges, R their distance apart, and C is a positive constant. Although this law was first published by Coulomb, it subsequently appeared that it had been discovered at an earlier date by Cavendish, whose experiments were much more refined than those of Coulomb. Cavendish was able to satisfy himself that the law was certainly intermediate between the inverse 2 plus 1/50 and 2 minus 1/50 power of the distance. Unfortunately, his researches remained unknown until his manuscripts were published in 1879 by Clerk Maxwell. The experiments of Coulomb and Cavendish, it need hardly be said, were very rough compared with those which are rendered possible by modern refinements of theory and practice. So that these experiments are no longer the justification for using the law expressed by Formula 1 as the basis of the mathematical theory of electricity. More delicate experiments with the apparatus used by Cavendish, which will be explained later, have, however, been found to give a complete confirmation of Coulomb's law. So long as the charged bodies may both be regarded as infinitely small compared with their distance apart, any deviation from the law of Coulomb must accordingly be attributed to the finite sizes of the bodies which carry the charges. As it is only in the case of infinitely small bodies that the symbol r of Formula 1 has had any meaning assigned to it, we may regard the law 1 as absolutely true. At any rate, so long as r is large enough to be a measurable quantity,